Welcome back to part 6, example 4. Let's get straight into it. Here we have a 3 meter long box beam with a point load in the middle, and it's a permanent dead load. The boxed up section is made up of 4 planks of wood, and the material is MGP10 in this case. Okay, and here we have 3 configuration of the boxed up beam, A, B, and C, and the aim of this presentation is to determine which fixing configuration provides the highest shear strength capacity. Which one do you guys think? Okay, I've also numbered the fixings as F1, F2, F3, and F4. If you have noticed here, because of symmetry, shear stress on F1 are all the same, and the shear stress, here we have also 4 horizontal planes passing through the fixings. The shear stress on F2 are the same because we have 2 horizontal planes passing through the fixings, and it is symmetrical. And F3 in this case is 2 vertical shear planes passing through the fixings. And finally F4, again, they're all the same, and because we have 4 vertical shear planes passing through the fixings. Let's talk a little bit about that in details. Now, let's quickly move on to the beam loading and fixing information. Okay, here, what do we have? Okay, we said that the beam length was 3 meters. The factored strength the factored load for strength is 4 kilonewton for the loading combination of 1.35 G. That's around 400 kilograms, say. The timber joint group for MGP10 is JD5. For the sake of this example, we will ignore screw capacity for direction of load parallel to the grain and the end grain. I think I've taken in this case to be just perpendicular to the grain, and I've also taken the embedment depth of the screw to be around 35 millimeters. So single number 14 screw, which is around 6.3 millimeters, is approximately 1 kilonewton. Okay, and we will take just one value for the sake of simplicity, for the sake of this example. The timber shear stress capacity is given to us as 1.25 MPa, and that is a factored capacity. Now have a think of why I've put the timber shear stress capacity in this problem. Okay, we will go through it towards the end of the video. You'll see why. This 1.25 MPa was based on K1, the K1 factor of 0.57, the load duration factor. Okay, and that is for the loading combination of 1.35 G. Okay, now let's look at the beam model. Here we have a simply supported beam with 4 kilonewton in the middle. Therefore, FYA is 2 kilonewton, FYB is 2 kilonewton, half of that middle load. There is no external horizontal forces, therefore FXA is 0. Shear force, we go up 2 and then go straight to the right up until we reach the point load, and now we go down 4 kilonewton and then move to the right to the end of support B and then go back up another 2 kilonewton. Okay, so the V star, the maximum design shear force we will consider is 2 kilonewton. And this is for the formula of VQ over I, the shear flow. So remember that. That's why we need the maximum shear force. Great, now let's look at the design option A. Okay, here we have the horizontal plank dimension is 290 by 45, and the vertical dimension of this plank is 200 by 45. The geometrical centroid of the whole section is 145 millimeters, which is 290 divided by 2. And Y bar in this case is 122.5 millimeters, so that is the distance from the geometrical centroid of the whole section to the centroid of this upper area here. But we will talk about y bar a bit more later. So the first question we would ask ourselves is, where do I take Q? And this is probably the tricky part. Where do I take Q about? There are 4 main steps that I usually take, and it hasn't failed me yet. So these 4 steps seems to be consistent across almost any problem. The first step is locate the shear plane where fixings are positioned in respect to the centroidal axis. So you need to look at the section and say, okay, where are the shear planes? How many shear planes do I have through the fixings? And what are their location in respect to the centroidal axis? Number 2, symmetrically shear, so symmetrically cut through the entire plane, right, throughout the cross section. The third step is then separate the sheared section that you sheared through, separate it from the rest of the members. And then the fourth step is take Q, the first moment of area, around the separated section. I know there's too much to unpack here, but we will go through it step by step. Okay, now let's see how we can do this for option A. Right, here we have fixings F1, and they're all the same around this corner of this box section. Now what we need to do is, at the fixings, we will shear right through the cross section through the fixings. So how many shear do we have? We have 1 shear that's going right through the fixings. And when we shear, we need to shear right through the cross section throughout the entire beam. Okay, this is the idea. So we can't shear halfway. Shear means you cut through the entire cross section throughout the entire beam. All right. So if we go through the top, we will shear right through, and that shear above the x-axis, which is the horizontal axis, the major bending around the x-axis, that shear will be symmetrical to the shear below the x-axis. So if we shear at the bottom, it will be the same thing. So we can shear it at the top or the bottom, and we can take Q, this hatched area, right, from that top, or we can do the same thing from the bottom, one or the other, and that will be around the major axis. So in this case, if we shear right through the fixings, then A bar will be 290, right, by 45, and that would be 13050 millimeters squared. Y bar in this case is 122.5. Okay. Q is the product of A bar times Y bar, and that will give us 1598625 millimeter cubed. Now I is simply BD cubed of the entire section minus the hollowed area here. Okay, so that will be 290 times 290 cubed divided by 12 minus the inner area here, which is 200 by 200 cubed divided by 12. Now that doesn't change for all the options. I seems to be consistent throughout the entire presentation, basically. All right, so we got that. Then Q is simply the shear flow. The shear flow is VQ over I. Remember the V, which we calculated before, that's 2 kilonewton. We multiplied that by 1000 to convert everything to Newton, times Q, which we have just found, divided by I. Okay, and that will give us 7.01 Newton per millimeter. So that means we have 7.01, so 7.01 Newton per millimeter shearing through the fixings right through the beam. So that means each plane will take half of it. So 7.01 divided by 2, that will be 3.51 Newton per millimeter. Okay, now let's see how many screws are required and the spacings needed. Okay, so the number of screws required will then be 3.51, which is the shear flow for each plane, multiplied by the length of the beam, divided by 1000. Now 1000, because we were given the capacity per screw is 1 kilonewton, we converted that to Newton, okay? So we need 10.53, so we rounded that up. So we need about 11 screws for F1 in each corner. 3000 divided by 11 will give us about 272 millimeter centers. We can round that down to 270. So therefore F1 will be adopt number 14 screws at 270 centers in each corner. Now let's move on to design option B. Okay, we have to go through these 4 steps again, and I will keep repeating it throughout the presentation, but it is important. So we go through the 4 steps and we can see then how we can pick this problem apart. Now this problem, option B, is a little bit trickier than the rest of them. So the main question again becomes, where do I take Q about? Number 1, locate the shear plane where the fixings are positioned in respect to the centroidal axis. In this case, we have F2, horizontal shear plane passing through the fixings, and F3 we have a vertical shear plane passing through the fixings. So the question then becomes, how many shear cuts do I need to do? And then the follow-up question then becomes, how many shear cuts would be above and below the horizontal axis, or with the major bending, the major axis? So how many shear cuts would be above and below this x-axis? Okay, let's have a look. So now let's see how this can be done. We have F2, horizontal, is a horizontal shear plane, so we will need to cut through that. And as we're cutting through, at the ends there, we are not cutting through the fixing where F3 is, because F3 is a horizontal fixing. Okay, F2 is a vertical fixing. So we need to cut through that vertical fixing and continue cutting through. And at the end here, where F3 is, guess what? We are cutting through the timber. Okay, we're not cutting through our fixings. We're cutting through the timber. So then, where do we take Q about? This hatched area here. Okay, so put in mind, we need to share, there will be the same shear flow, but this time the shear flow will be distributed in the fixings and in the timber capacity, and in the timber. So you can imagine that shearing the timber is a lot more than shearing through the fixings. But let's see how we can do this. So A bar in this case will be 290 by 45, same as the previous example in option A. But then the other question we ask is, how many shear cuts did we go above the x-axis? Only one shear cut that went right through, just one. So Y bar in this case is the same as the previous example, 122.5, everything is the same. And Q is the product of A bar times Y bar, which is 159.8625 millimeter cube. I is the same, and then the shear flow will simply be 2 times 1000, converting it into Newton, times Q divided by I, and that will be 7.01 Newton per millimeter. And then each plane will take, again, 7.01 divided by 2 will be 3.51 Newton per millimeter. But we have a factored shear stress capacity of this timber of 1.25 MPa. Now the capacity to shear off a 45 millimeter thick timber is 1.25. Remember, MPa is Newton divided by millimeter squared, okay? So 1.25 times 45 will give us 56.25 Newton per millimeter. So to shear this 45 millimeter off, you need 56.25 Newton per millimeter. That's how much force you need, okay? And the timber alone in that 45 millimeter thick has almost 8 times the capacity of the total design shear flow. So, for example, 56.25 is much greater than 7.01 Newton per millimeter. So we can probably nominate nominal fixings for F2 and still be satisfactory. The nominal spacings as per AS 1684 is 2 times the beam depth, where the beam depth is obviously parallel to the loading. So we can say, okay, F2 can be at 580 millimeter centers, right? And if the fixings failed at F2, there will be enough shear stress in the timber alone, okay? Or to be conservative, and everyone can sleep at night, and I kind of encourage the conservative approach, is to ignore the timber capacity completely and assume that there is another screw, another F2 if you like, another vertical F2 on the other side, on the other end. So then the number of screws required would simply be like option A, 3.51 times 3000 divided by the capacity per screw. We need 11 screws, and then 3000 divided by 11 will be 272. Okay, so 270 millimeter centers. Rather than making it at 580, we can just do it at 270 centers. And this is probably a nice conservative approach, and everyone is happy at the end. Now, what about fixings F3? How do I take Q for fixings F3? Same idea. We need to look at the shear planes for F3. We have vertical shear planes. Now, that means we need to shear vertically through the fixings of F3. But hang on, if we shear at the bottom, so we have on the bottom left-hand corner a vertical shear as well. So we need to shear, how many shear do we need to do? We need to actually shear it twice this time. So we shear the right-hand side, right down, and it's going to go through the timber. And then on the left, we also shear vertically. So there's 2 shears. Then we take the first moment of area between the 2 shears. You get the idea? And the shear cut, is, if you noticed, is symmetrical. Okay, this is the trickiest part of the whole problem. Okay, so that means what do we take for Q? The A now in this case will be 200 by 45, because the member that's taken between the 2 sheared section is only 200. So that'll be 200 by 45, that's the area. Y bar is still the same, 122.5. And Q this time is a little bit different, because A is much less than the previous example. So that would be 9,000 multiplied by 122.5, okay? And that would be 1102500 millimeter cube. I is exactly the same. The second moment of area is exactly the same. Shear flow is 2. Again, the shear force, the transverse shear force, the vertical shear force is exactly the same. So 2 times 1000 by Q divided by I. This time we have 4.83 Newton per millimeter, and that's the total shear flow between the fixings, okay? So therefore, each plane will take 4.83 divided by 2, and that will be 2.415. But then again, because it's going through, that vertical shear is going through the fixings and the timber itself, the fact that shear stress capacity was given to us as 1.25 MPa. Now, so 1.25 times the thickness of 45 will give us 56.25 Newton per millimeter. In this case, timber alone, in the 45 millimeter thick, has almost 11.5 times the capacity of the total design shear flow. So 56.25 is much greater than 4.83. Again, we can probably get away with nominal fixings for F3 as well. So 2 times 290 is about 580 millimeter centers. Or we can be conservative and make life easy and and find the number of screws, pretend that there is another horizontal screw for F3 rather than using the timber. So assume that there's another screw there, and then the number of screws required will be 2.415. Okay, that's the shear flow for each vertical plane. 2.415 multiplied by 3 meters divided by 1,000, so 3,000 millimeters divided by 1,000, which is the screw capacity. That will give us 7.24. We can round that up. Always round it up to the number of screws. It's more conservative that way. And that will be 8 screws. Therefore, 3,000 divided by 8. And that will give us 375 millimeter centers. So for F3, we can adopt number 14 screws at 375 millimeter centers each end to each end. It is a little bit less than 580, but then again, being conservative will always put you in a better position. Okay, finally, let's check out the design option C. Now, I'm guessing by now you've memorized the 4 steps required. Okay, so this is a lot easier. This is very similar idea to the option B, but in this case we only have vertical shear cuts. Okay, there is no horizontal shear cuts because you can see that the fixings are all horizontally, so we are shearing right through the vertical planes. So let's see how we can work this out. Okay, we have, so we ask ourselves, how many shear do we need to cut? Well, there will be 2. We will cut one through the left-hand side and we'll cut one through the right-hand side. Okay, so Q is taken around this hatched area here. A bar in this case will be 200 by 45. That's 9,000 millimeter squares. Y bar is the same, 122.5. Q is 9,000 multiplied by 122.5. Okay, and then I is the same. Shear flow in this case will give us 4.83 Newton per millimeter. Again, each plane will take 4.83 divided by 2. That's 2.415 Newton per millimeter. And how many screws do we need? Similar to the previous problem, it will be 2.412 multiplied by the length 3,000 divided by 1,000. And that will be 7.2, so we round it up to 8. Again, 3,000 divided by 8 will give us 375 millimeter centers. Okay, so F4 will be adopt and number 14 screws at 375 centers to each corner. Wow, so which design option would you choose? I would definitely go for design option B because we are shearing through the actual timber itself vertically and horizontally, a much greater shear strength capacity. And then after that, I would move to option C. Again, we had screws there at 375 centers. That is the second strongest. And then the third strongest will be option A. Wow. So this brings us to the end of my shear stress and shear flow story. If you have enjoyed this series and you have found it useful, please like, share, and subscribe so that others may also learn. Until next time, we hope that you have a great afternoon.